Well, then let's get started. Uh, the last talk is by our pretty renowned by now, Aaron. And the topic is going to be, hello, Aaron. How are
Hello.
you?
I'm doing well. How are you?
I'm doing also well, thank you. No cat butts on the on the screen, so well, not from my
Yeah,
side.
same here.
Not from yours. Oh, cool. Oh, cool. And enjoying the sun. Still hanging in there until I hope tomorrow. So, yet another day of summer. Yes, yes, we can do it.
Nice, nice.
Yeah. I was about to say that your talk is going to be about garbage collector, and this a little bit reminds me of kind of like a Marvel franchise. I've been seeing talks on garbage collector from you since I think 3 or 4 years now, and it's generally great because as I was saying before with someone else in the hallway chat, seldom you get as a in your daily job to go and look at the internals of something that you use on a daily basis. And I've always appreciated the insights that I get from your talks, beside the fun, of course.
Oh, thank you.
Um,
Thank you. Yeah,
Absolutely.
I like talking about GC and looking at it because I think it's kind of a oh, sorry, I brought my
Those are tools that you
yes.
use for your job. It's
This is how I
important.
type. Yeah.
I wonder what Ivan has to say about that. Um,
So I like looking at the GC and talking about it because it's like this thing that's always there working, like doing work for us, but like we don't ever have to look at it. We don't have to like mess with it very much until sometimes we do, and then it's like, oh boy.
oh boy,
So
it's perfect.
yes.
I think it's everybody has that kind of sentiment looking at it. Fun fact: a question on GC was the only technical question I got on my interview when I interviewed for my current company. I was like, "Isn't this supposed to be a technical interview? How does Ruby deal with memory?" And I was writing something. I was reading something else, and the garbage collector. What kind of question is that?
Yeah,
But
that's a weird question. Yeah.
I was like, "Are you really sure you are a Ruby developer?" I guess so. Uh, anyways, um, well, this is going to be a pre-recorded talk for the people in the chat. They know already. They're going to post questions there. If there are any, I'm going to read them to you afterwards. Just be funny, people. Come on. Oh, the bar is pretty high here. I leave the stage to you then.
Hi everyone. Today I'm going to be talking about reducing memory by using more. Actually, I'm mostly going to be talking about concurrent and automatic compaction in Ruby, but I thought that the other name was much better, so I wanted to use that name instead. Actually, I am going to be talking about reducing memory by using more, but the main focus will be on automatic concurrent compaction today. Hi everyone, welcome to Rubyday. I really wish that I could have come in person, but I guess the good news is that since I can film from home, you can actually see my cat. Hey buddy, say hello to everyone. Oh, hello. Okay, I think he's done. All right. My name is Aaron Patterson, and I'm known on the internet as Tenderlove, but you can just call me Aaron too. It's really fine. This year I started a new job at a company called Shopify, and I'm a full-time Ruby and Rails contributor for the company. And I feel really, really lucky to have this job, and I just wanted to say, like, I'm really happy. I get to work on Ruby and Rails, like improving the language and the framework all day. So I just want to say thanks, like thanks to Shopify, and it's really a dream come true for me. So In this presentation today, actually, I want to talk about the developments that I've been doing, or the work that I've been doing at work on Ruby, and the progress and process that I've done so far. So, as I said, I'm on the Ruby and the Rails core team, and I'm employed to be a Ruby and Rails contributor. And I'm also the inventor of the analog terminal bell. And I don't know if you have seen the ad for this, but if we have time, I may play it. And anyway, let's get into the presentation. So in Ruby 2.7, I introduced a feature called gc.compact. And this feature allows us to save memory by filling in spaces in our heap. So if we have like extra, unused areas in the heap, like it's fragmented, we can kind of fill in those spaces and use them. So it's a technique called eliminating fragmentation. And if you recall, like this program, it's this DOS utility program from a long time ago. It would defrag your hard drive, so it would like fill in any unused spaces in your hard drive. This is basically the same thing, except instead of your hard drive, it's filling in spaces in your memory. So compaction allows us to reclaim memory that's not being used. And this program, so this sample program, it demonstrates the effectiveness of compaction. So first off, it loads a Rails application into memory. Then it runs the GC to remove any garbage that was created while loading all the code. And then it compacts the heap to remove any spaces in memory. So here's an image of what the memory layout looks like before compaction runs. The green and the black dots are objects and the white dots are free space. And after the compactor runs, it looks something like this. Now this is the layout. So this is the layout after the compactor runs. Green and black dots are regular objects, and red dots are objects that couldn't be moved. In this graph, the objects are much closer together, so you don't see as many white spaces between them. And it's kind of hard to see, but actually the graph is more narrow than the previous one, and that indicates that we're consuming less memory. So before we dive into my current work, I want to cover the existing compaction algorithm, the one that's in Ruby 2.7. The compaction process has two steps. The first is to move objects, move them closer together, and then the other one is to update all of the references. So imagine that there is a memory layout that looks something like this. The blue squares represent Ruby objects, live Ruby objects, and the white squares represent empty slots where we could store a Ruby object. And yellow represents a forwarding address. So the compaction process, again in Ruby 2.7, requires two pointers, one at either side of the heap, one at the beginning and one at the end. One of them is called a free pointer and the other one is called a scan pointer. And the free pointer scans right until it finds a free slot. And then the scan pointer, it moves left until it can find an object, a filled slot. So when it finds a filled slot, it swaps the two. So they get swapped around like this. And then it writes a forwarding address to the old location. So in this case, the object in slot 9 moved to slot 3. So we write a forwarding address of 3. So we just repeat this process of looking for empty slots, and then looking for filled slots and swapping them and writing addresses. And we repeat that process until the two pointers meet, and then we know that we're done with the movement process. So here's the same heap layout before compaction. Now some of these objects have references to each other, and maybe it looks something like this graph. Now when the objects get moved around, the references will actually go bad. So for example, here we have some of the references have gone bad, so we need to update all the references. And to do this, we simply iterate over the heap, checking the reference and then updating it. In this case, object 1 references object 7, but the object that's at 7 is now at 4, so we have to update that reference to point at 4. Then the next object 2, it's pointing at 6, we have to update that to point at 5, and then we just keep repeating this process. We look at each object and see what references it has, and if those are pointing at forwarding addresses, we need to fix up those references. So we just repeat this process for every single object in the heap. And once that gets to the end, we're done with the reference update process. And finally, when we're done with that, we can clear out all the forwarding addresses, and those become just empty slots again. And now we're done compacting the heap. So that's the existing algorithm on Ruby 2.7. So as far as compaction itself is concerned, I want to talk about like what my personal goals for that feature and project are. First off, I wanted to save memory, and this is probably the most important goal because I mean, why like we want to save memory. That's important. I also want it to be automatic, so like I don't want developers to know that it's happening or to have to say like compact the heap specifically. It should just happen automatically and just work for you. And I would like it to be concurrent as well so that your program can run and then we can compact the heap and then let the program run a little bit more. But the idea behind adding concurrency is such that we can do this without pausing your program as much. And finally, I want it to be fast as well. So I'm going to discuss each of these goals and where they are. So first, let's talk about saving memory. Here is, in this slide, we can see two graphs. One of them is, they're the same two layouts that we saw before. The top memory layout is a layout of a Rails application before we've compacted the heap. The bottom one is one after we've compacted the heap. Now, we can see by comparing these two graphs that we've saved memory because one of them is the compacted heap is actually more narrow, so we were able to free up some space. And the other, the compacted heap also has all the objects much closer together, so there's no free space in between them, and that helps with copy on write performance. So I think that we can say, like, we can already say that the very first goal is met. We do save memory. So let's look at the next goal, which is automatic, making the compactor automatic. So I want to make the compactor automatic because I don't think that the developer or anyone should have to know that it's running or run it specifically on its own. It should just happen for you. But today you have to call gc.compact in order for the compactor to run. So this is clearly not meeting this goal. Usually we run it like this. We'll load our entire Rails application, then we'll compact the heap because we've got all that code that's going to stay there. It's going to stay there until we kill the process. So we load all the code, compact the heap, and then fork all of our web servers. But we have to call gc.compact ourselves, so this is definitely not automatic. So this goal is not met. Now concurrency, and we have to call gc.compact ourselves, so we already know the answer to this goal. It's not met. It's definitely not concurrent because we have to do it specifically. But I do want to talk about take this opportunity to talk a little bit about an implementation problem, and that is when objects are moved, the destination slot has to be empty. And this doesn't really sound like a problem, but it means that the GC steps have to happen in a certain order. And if we want to do this concurrently, we have to change the order. So as I said earlier, the compaction process has two steps. First is moving the objects, and the next step is updating references. But since we can only move objects into empty slots, it means that the sweep step has to happen before the compact step. It's a requirement. So we have to have the sweep step happen before the compact step, and of course the mark step has to happen before the sweep step. So we have to call gc.compact ourselves, and the GC steps require a certain order, so this is definitely not concurrent. Finally, the last goal, speed. I mean, I think speed is kind of a relative issue. Like how fast is compacting the heap? Like maybe it's fast. It depends on what you're comparing it to. But we can't really, like, in my opinion, I don't think we can actually talk about speed unless we have concurrency. Because if you have to call gc.compact when as you're booting your application, it doesn't actually matter how long it takes because you're not going to be serving any requests until the process is actually up and running. So speed, we can't really say whether or not it's fast right now. However, making the compactor automatic and also making it fast both depend on making it concurrent. And making it concurrent is the goal, like that's the topic, the thing I would like to talk about today. So when we say concurrent, we have to be concurrent with something, like running concurrently with something. And what are we talking about? Like when I say running concurrently, what are we running concurrently with? Ideally, it would be best if we were running concurrently with Ruby code. That way we can reduce the amount of time your program pauses. So we can let your program run and then compact a little bit and then run and compact a little bit. But that's really too hard for my very first try. Like it just sounds way too hard. And I don't like doing hard things. So I wanted to start with something a little bit easier. And I've decided that instead of making it concurrent with Ruby code, instead I thought I would start by making it concurrent with the sweeping step. So for the first implementation, we'll change the move step to be concurrent along with the sweep step. So instead of a process like this, we have a process like this, where we make the sweep step and the object movement execute at the same time. So let's take a look at the sweep process and then talk about how we can integrate the move process. I'm not going to explain the marking step of the GC, but after the marking step, any objects that we will keep will be marked, and that's indicated by the mark bits along the top. We keep a bit table of marking bits that indicate whether or not an object is marked. So anything that is marked will be read, and we can't release those. Those are live objects. And anything that's not marked, those things we can sweep. So all of the white bits. So the next process is to look at each object, and if the object is marked, we just leave it alone and we move on to the next one. But if the object isn't marked, in that case we're going to free the object. So we free that up and we can reuse that slot later for another object. We just repeat this process, looking at each object, seeing whether or not it's been marked, and then we're freeing it if it hasn't been. And we just iterate this process as we go through the heap. Now let's take a look at how we can combine the sweep step and the move step. Hi, yes you are a good cat. So let's look at how we can combine the sweep step and the move step. The sweep cursor looks very similar to the free cursor, so we should be able to combine these two processes. It's just moving from one side to the other, examining each object. So the first thing we do is just add a scan cursor, like we had in the original algorithm. So we'll add a scan cursor here. Now the sweep step remains exactly the same. It's just looking at each object and its mark bit, but after freeing an object, instead of immediately moving on to the next one, we'll use the scan cursor to search backwards and look for an object that we can move into that slot. So we have the scan cursor move one in, we write a forwarding address, and this looks exactly the same as the previous compaction algorithm, but we were able to combine movement along with object freeing. Now, when the two cursors meet, we know that this particular page, we know that the heap has been compacted just as before. Now, when they meet, we pause the sweep step and we update all the references. So reference updating isn't concurrent, we have to stop everything, but we're able to do movement and sweeping at the same time. So while the sweep step is paused, we update references exactly the same as we did in the previous compaction algorithm, where in this case one is pointing at 6, and we need to fix that up to point at 5, and then 2 is pointing at 7, and we need to fix that up to point at 4. So we just repeat this process as normal, just like the original compaction algorithm. Now, after reference updating is finished, we just continue the sweep step as normal. And what's really nice about this is that the sweep step automatically frees any of the forwarding addresses for us. It cleans those out. So we see that the forwarding address isn't marked, so the sweep mechanism just go ahead and frees them up and adds them back to the free list. So once the sweep step finishes, compaction is done. Yay! So I implemented this algorithm and it seemed to work fine. So everything seemed to work. I sent a PR. You can see it at this URL. The CI passed. Everything seemed good. So I merged it. I thought everything was fine, but then after I merged it, CI started failing. We were getting other failures in CI. So I ended up having to revert the patch. So we are currently not concurrent. So I went to investigate what was wrong, like what was happening. The algorithm seems fine. Like when we think about the algorithm, it makes sense. But it took me a while to figure out what the bug was, but I'm going to describe what it was. So let's say in Ruby we have like maybe 3 classes like this. And in the implementation of these classes internally, so say we have class A, B, and C are subclasses of A. Internally, Ruby tracks the class parents and children. So class A knows its children B and C, and class C and B know their parent A. Now, if class C gets deleted, then the GC frees C, and class C needs to remove itself from class A's child list. So when C gets freed, first off, we have to remove it from A's child list, and then we can free up C normally. That means that during the GC sweep phase, class C has to access class A's memory. So let's take a look at the same process, but from the perspective of the garbage collector. The sweep cursor moves along until it finds class C. Class C is not marked, so class C needs to be removed from A's child list. So it removes itself from A's child list, and then the sweep step goes ahead and deletes class C. Okay, now I want to look at we're going to go over this one more time. Exactly the same process, but this time we're going to add the compaction algorithm in. So the process for sweep and compact is almost the same as it was for sweep. So sweep moves along and we find an empty slot. So the scan pointer moves along and it moves A. It moves the class A and leaves a forwarding address. And then all of a sudden when sweep gets to C, we have an issue. So sweep gets to C and we want to free up class C. So class C needs to remove itself from A's child list. So it says, okay, I'm going to go look at my parent and then remove myself from my parent's child list. Now the problem is that C is now pointing at a forwarding address. It's not actually pointing at class A anymore. So it tries to remove itself from class A's list only to find that there is a forwarding address there and it doesn't know what to do with that because reference updating hasn't occurred yet. So it accesses the forwarding address, treats it as a class, and then all of a sudden the program blows up because this isn't a class, it's a forwarding pointer. So if we look at the crash, I put the debug logs into the commit, like the revert statement. If we look at the crash, we'll actually see that, yes, in fact, this child class, if we look at its parent, it's pointing at a moved address. So you can see this R moved here. So what do we do about this problem? Up to this point, I assumed that when an object was freed, it would only free its own memory, like it would only touch itself. So like, I would really like to put a restriction on the objects and say like, well, if you free, you can't touch, you can't look at any other objects. You can only mess with your own internals. But of course, I can't do that because there must be other objects out in the wild that do something similar. So I don't want to break an existing code, so there must be some kind of way to fix this, and the way I chose to fix this was to introduce read barriers. And what are read barriers? Read barriers are just functions that are called when something gets read. So here's a very simple example of a read barrier. It intercepts reading an instance variable. The read barrier just takes an action when somebody tries to read something. So for example, if an object is going to be read, we can have a chance to do something. So in the case of our GC bug, when C tries to read A, we can intercept at that point before it gets to read A, and we can move A back into position. So unfortunately, read barriers have a few problems. First, they're pretty complicated. Here's a very simple program. Let's find all the spots in this program where we have to add a read barrier. Of course, we need one when we read the instance variable foo. We're going to need one when we add initialize to the foo class because the foo class might move. Same with when we add the method bar to the foo class. They might move, foo might move, and then we need it on when we call new, and we need it when we call bar, and we need it when we set the instance variable. But like, this may not even be all of the places where we need read barriers, but the point is we have to add them in a whole bunch of places. It's very hard to know where to add all of these things. And it's just way too complicated for me. The other problem is, if we have to add these read barriers in all these places, it can actually slow down our program because every time we do something, we have to check, oh, do we need to execute the read barrier? So it can possibly slow down our program. Now, this type of implementation is treating this type of read barrier is treating our program as a kind of graph where it protects the integrity of this graph. So if the instance variable moves, then when the reference is read, the read barrier could actually execute and fix up that location right at that time. Now, this can be very powerful, but it's also very difficult to implement and can slow down the program. And the thing is, I'm just very lazy, and so I want to do something easier. I chose to use the mprotect system call. This is a function that allows us to protect a region of memory. We can mark a section as having no access. Now, if anything tries to access that section of memory, we get an exception and we can do something at that moment. So let's see how this will fix our bug and then talk about the mprotect function. This works the same as the previous algorithm, but after we move an object, we protect the page that object came from. So each time we move an object, we remove protection and then we add protection again. So now this slot 3 or slot 9 is protected. Okay. So at this point, when C tries to read the address 9, it's looking for class A, tries to read address 9, an exception occurs because that region of memory is protected. So after the exception handler, what we do is we intercept that exception and then remove protection from the page and move all of the objects back to their original locations. So we'll move everything back. Now we let the sweep step continue as usual, and A is actually back in the right place again, so C can remove itself from A, and we move on, we do the sweep step just as normal. So there are some problems with this system call. Protected regions 4 kilobytes, so that means the beginning address needs to be divisible by 4 kilobytes. And the size must also be, the region of memory that we're protecting, that must also be divisible by 4 kilobytes. So let's see if we actually meet those requirements. This is the code in Ruby where a page of objects is allocated. This is the region of memory that we want to protect. So it actually aligns on a constant called heap page align. And heap page align, the value of that is 1 shifted left 14. And that value is 16384. And that number is divisible by 4 kilobytes. So this works. So we know the address is a multiple of 4 kilobytes. But what about the size? Heap page size is this constant. The size of it is stored in this constant, heap page size. So that's the alignment minus required size by malloc. Required size by malloc is the size of size t times 5, and just a bunch of different calculations. And if we do all of those calculations, we'll see we come out with this value, which is about 16 kilobytes minus some amount. And that is not divisible by 4 kilobytes. So we have a problem. The size is not a multiple of 4 kilobytes, so we can't use mprotect in this case. But this started to make me think, why not just use exactly 16 kilobytes? If we can allocate 16K, then I can use mprotect. And another interesting thing is that required size by malloc is the same size as a Ruby object. It's 8 times 5, which is 40, and a Ruby object is size 40. So if we allocate exactly 16 kilobytes, then each Ruby page can store 1 more object. So I sent a patch to extend heap pages to be exactly 16 kilobytes. To test the patch, I used RDoc generation as a benchmark. I generated RDoc and recorded the process size as it was the amount of memory it's using as it's generating RDoc. So this is a graph of the memory usage over time. The x-axis is time and the y-axis is the amount of memory that the process is using. The red lines are the master branch and the blue lines are the branch with my patches applied. I ran the benchmark 50 times, so there's 50 red lines and 50 blue lines. And from the graph, we can see that when the patch is applied, we're typically lower. The blue lines are typically lower. Here's another graph. This is the maximum RSS, or the maximum amount of memory the process used. On the left side is master, on the right side is our branch. And from this, we can see that the median memory usage with jemalloc is typically lower. So on average, we actually use less memory. What these graphs are saying is that when we request more memory from the operating system, we actually use less. So we use less memory if we request more, which is pretty counterintuitive. So the question is why? Like why is this the case? The reason is that jemalloc has fixed size buckets where you can allocate memory, and 16 kilobytes is one of those bucket sizes. So if you allocate something just short, say 16 kilobytes minus 40, jemalloc will reserve an entire 16 kilobytes for you, but that 40 bytes goes wasted. So we end up storing Ruby objects on most of that page, but then we have 40 bytes that are just unused. However, if we allocate exactly 16 kilobytes, then the entire block is used. So allocating a good size chunk of memory will actually help us reduce memory usage on average. It'll help us reduce it overall. So this is why I called the talk Reducing Memory by Using More. So I thought that was a very interesting discovery. So this is the whole patch. The important part is here where heap page size is now the same as heap page align. So now pages are aligned at 4 kilobytes, and the size is also a multiple of 4 kilobytes, which means we can use mprotect. I made a pull request here that uses mprotect to implement a read barrier and combines compact and free, or compact and sweep. And the read barrier works very well, except that unfortunately it's turned out to be way too slow. When I compared the read barrier to just like compact with a read barrier to just regular compact before the read barrier, it turns out it was actually 4.5 times slower than the original, and that's just not great. I don't think that 4.5 times slower is that good. So now the compactor is concurrent, but I guess like since it's gotten slower, I don't think we can say it's fast. So even if compaction is concurrent, making it 4.5 times slower is just too slow. So like, what can we do? What can we do to speed this up? Of course, like whenever I have to speed up some code, I profile the code, and typically in Ruby code, I'll use stackprof. But in this case, we're not actually profiling Ruby code, we're profiling Ruby itself. I guess we're profiling Ruby code, it's just the code that we wrote Ruby with. So we're not profiling Ruby code, we're profiling Ruby itself, and Ruby is just a C program. So rather than using stackprof, which is a Ruby code profiler, we need to use a C code profiler. And I am going to use, like, since I use macOS, I usually use instruments for doing profiling on C programs. So I'm going to give you an example of how to profile I'm going to show you how to use it. This is the command that I use, and I've broken it down into several lines so that we can talk about each part of the command. First, we just have the instruments command itself. You just run instruments. You have to tell instruments what profiler you want it to use, and in this case, we're doing a time-based profiler, so I have to tell it time profiler. Then we give it the target program, and in this case, we're profiling Ruby, so we say Ruby, and then we also give it any arguments to the program, so we're telling it, I want Ruby to run these with these command line options. Now, when you run it, it'll leave a directory behind, and that directory has all the profiling information, and we just have to call open on that directory. When we call open on the directory, it'll open the instruments tool. So this is what it opens when you open the directory, and if you can click through the stack traces and see that where the bottlenecks are, and in this case, the bottleneck is actually mprotect. We're spending all of our time doing calls to mprotect. So that is our bottleneck. So I usually have two strategies for improving performance. The first one is to make a function faster, and the second one is to just not call it so much. So in this case, mprotect is too slow, So the first one, speeding up mprotect, I don't think I can do that. I'm pretty sure that that's not going to work out very well. So I think that in this case I need to go with the second strategy, which is don't call it so much. So let's study the current algorithm. Before we move an object, we have to unprotect a page, and then after we move the object, we have to reprotect it again. So we're locking the page and unlocking the page, and we have to do that on every time we move an object. So we're locking and unlocking on every object move, and every lock and unlock is a call to mprotect. So in other words, we have to call mprotect twice per object that we move. So we're doing two calls to mprotect multiplied by the number of objects that we're moving. So the way that I chose to speed this up was to do batch object movement. So we really only need to unlock pages while we're moving objects. So if we can unlock the page and then move a bunch of objects, then we can amortize the cost of that mprotect across multiple object moves and save some time. And the natural place to do this is, a natural place to do object movement happens to be at page boundaries. So I modified the algorithm to only move objects after an entire page has been completely swept. So let's take a look at an example. To batch movements, we'll sweep a page without moving any objects. So we just sweep the page as normal without moving anything. Now, once we get to the end of the page, then we're going to introduce a free pointer, and when we get to the end of the page, the free pointer will look for an empty slot, and then we'll do the same thing with the scan pointer where we unlock a page, look for an object, and swap, and then we move the free pointer and then until it finds an empty slot, and then we move the scan pointer again until it finds an object, and we swap them. And then once the free pointer meets the sweep pointer, well, then we know we're done packing that particular page, and we can lock that page that we were moving objects from, the source page. So I want to point out two things with this algorithm. First is the talk about the performance improvement. In the worst case, there's only one movable object on a page, which means that we'll have to do 2 calls to mprotect for one object. And this is the same as the scenario before. This is exactly the same as our performance before this improvement. But we're hoping that we can do better than that. In the best case scenario, we can move about 408 objects with 2 calls to mprotect, because one page can hold 408 objects. So in that case, we'll only call mprotect twice. So on average, we're looking at about 2 calls to mprotect per 200 objects. Now, this is actually really great. This is a 200% improvement over our previous algorithm. So if we implement this and we compare master to our branch with master has no read barrier to our branch with a read barrier but batched movement, we can actually see that the times are approximately the same. Like it's within a margin of error. So we're able to maintain the same speed as the original, but also introduce a read barrier. Now, the other thing that I want to point out here is that in order to speed this up, we basically had to revert the algorithm back to the previous algorithm. So it's not exactly the same algorithm as before, but it's basically the same. It's very, very similar. So instead of packing a whole heap at once, we're just packing one page at a time. So now that we have a read barrier in place and per page packing, we can actually make the compactor run automatically on major GCs. So we have a read barrier so we can know if anything tries to touch objects, and we can do one page packing at a time, which means we can actually make this run concurrently with a program. So I'm going to show the patch here for making it automatic and concurrent. And this is very anticlimactic, but this is the entire patch. It's a little bit upside down, but basically what we do is we say, okay, when we enter the mark phase, if this is a major GC, I also want you to do compaction. And then during the sweep phase, we say, okay, if this is a major GC, I also want you to do compaction during the sweep phase. Now we can actually see the compactor in action. If we run do gc.start, we'll do a full GC, and that implies a compaction because we just said we're going to do a compact on a full GC. And then on the second section below, we can see here that the program is just allocating objects until it kicks off a major GC, and that'll actually increase the compaction count. So you'll see in this program, we never specifically called gc.compact, yet the heap is getting compacted. So I want to wrap up here. It took me a lot of time to get this read barrier into place, along with the new algorithm that I wrote. And to be honest, like when I very first ran this program, like it was actually 27 times slower. So the very first implementation was 27 times slower than the original compaction implementation. But it turns out that that's because I didn't have optimizations turned on. So once I turned on compiler optimizations, then it sped it up, but it only sped it up, like it sped it up such that it's 4.5 times slower. So I guess the lesson is always turn on your, check that your compiler optimizations are on. Now, to be honest, I didn't really feel good about this project because it had gotten so much slower. I thought in theory it would actually be faster because we didn't have to iterate over the heap as much. But when I thought back on it, if I took a look at the bigger picture, the project wasn't really about speeding up compaction per se. The project was proving that we could implement a read barrier and make compaction concurrent. Now, the fact that I was able to prove that yes, in fact, we can implement a read barrier and make this concurrent, that was actually the win. Once I was able to accomplish that goal, really the only thing that was left is speed. And I shouldn't have been thinking about speed in the first place. I should have been thinking about just getting the project working. And that's actually where I want to leave off today. This brings me to the final point that I want to make, and I see this across like different projects all the time, and I want to point out that I'm actually a victim to it too, is that you need to make your code work and then make it fast. I think I fell into a trap where I thought, oh, I'll make this will definitely be faster, but that's not really the goal. The goal was to make it work. Once we make it work, then we make it fast. Thank you so much for having me. I wish I could have been in person this time, but next time I will definitely come. Thank you all again.
Hi, everybody. Oh, you are not happy, are you? Okay, okay.
Has this ever happened to you? CD space GIT tab. This must be the right directory. If only I'd heard the terminal bell. With the analog terminal bell, you'll never miss a terminal bell notification again. The analog terminal bell is a bell that rings anytime a bell character is displayed on your terminal. Simply plug it into USB. Then enable the analog terminal bell in your terminal settings. It works with your shell. It works with Vim. It even works with DevU Random. Thanks to the analog terminal bell, I'll never miss a terminal bell notification again. Go online and get yours today. Go to analogterminalbell.com today to get your very own analog terminal bell. Once again, that's analogterminalbell.com. Analog terminal bell is not actually for sale and requires a custom build of iTerm 2. Other restrictions may apply. See website for details.
Hello. The bell
Hello.
is just brilliant.
Thank you.
I was totally not expecting. Hello, there she is.
Aw, hi.
And damn it, not yet. But yeah, so we're gonna end up the day like this. I'm looking if there are any questions. Okay, the jokes in the chat have been gorgeous already. Anyways, was that really a microwave plate? That's my question to the whole talk, right? Like months of work, and the real question is, that's a microwave plate. Thank you. That makes me feel so much better.
I was trying to find, like, I wanted something to spin it on, and so I was like thinking, oh, it's the microwave. And I was filming it, and Abby was like, what are you doing?
I can totally imagine. Oh, I have another question. That's also my question. So, for the audience, we asked all our speakers to send us a bio to just, have an idea, maybe some point of conversations here and there. And there's one line in Aaron's bio that is about his interests, and it's like keyboards, cats, and code. Now, these are all hard C's, but when I looked at it and I read it, I was like, why a K and not a C like cheese? Your Twitter feed is full with cheese.
That's a good point. Yes. Bad joke should be my other interest.
I mean, the poor cheese. What has it done to you?
Yes, and cheese. Yes.
So now to the serious question. In the final version, Matteo is asking, concurrent is always meant with respect to sweep and move or other Ruby code. Also, what about the automatic part?
Yes. So actually, the final. So I have to admit, when I started the project, I was going to make it just concurrent with free, but actually, because I was able to implement a read barrier, it is concurrent with Ruby code as well. So it'll run alongside your Ruby code too. The main thing is that reference updating is not concurrent, so there's a pause for reference updating.
Thank you. Gregorio is asking, how does the cat feel about the analog terminal bell?
The cat, she doesn't mind it so much. It's mostly like when I'm ringing the bell, my wife is like, "What are you doing? So loud. Why are you doing?"
I mean, cats seldom ask questions. They more maybe are.
Well, so she like my one cat, Choo Choo. She'll sleep on my desk, and she'll like kind of sleep on the bell. So that kind of ruined. Like I can't ring it when she's sleeping on it.
I could, but maybe it's not a good idea. Anyways, so we are out of questions, serious and not. If you would have one advice to give to the people in the audience about getting started and looking into internally, if they would like to be you someday, where should they start?
Well, I guess so. It depends. I would recommend so if you want to start hacking on MRI, try writing a C extension, and then from there you can start diving into Ruby internals. One book I really recommend is there's a book called the Garbage Collector's Handbook, or people just call it the GC Handbook. If you find that, like, basically all the algorithms that I've explained, all the algorithms used in Ruby itself, they're all in that book. It's just like, it's actually really, I would say the stuff that we implemented in MRI is not really groundbreaking technology.
I mean,
it's like pretty normal. It's pretty well known. And this book documents all the algorithms, so you can read up on them there.
Perfect. Last question from Tiago. Is there any benchmark on big web projects?
That's a good question. So we've benchmarked it, we've benchmarked the memory savings. So we can see the memory savings, and it's around 10% or so. But that depends on like what kind of objects you're allocating. As far as like automatic compaction, I haven't benchmarked, so I don't know what the impact is to speed in that case. So we got to figure that, like, that's an upcoming thing. The other thing too, though, is we have to keep in mind it only ever runs on major GCs, which if you tune the GC correctly, major GCs should be very infrequent. So the performance, like, maybe it's a little slower, but it shouldn't matter in the, like, overall scheme of things.
Okay. Thank you so much for your time and for being with us today.
Yeah, of course. Thank you for having me.
Thank you.